In the last lecture, I left with significance of shape factor. I have shown the shape factor for the rectangular section. Now our next topic is collapse load of a structure. The collapse load of a structure, in this we find at which maximum load the structure will go under failure. Either it's a beam or it's a frame. Collapse load is found for a structure by investigating various possible collapse mechanism of a structure under conceivable load systems. Means if in a system there is a point load UDL, okay, we will find multiple mode of failure. Means we will find the load which will cause the failure of the structure in the collapse load of structure. For any given mechanism, possible plastic hinge locations are determined by noting the types of loads and support conditions. Remembering that under increasing loads, the plastic hinges would form in the sequence defined by corresponding elastic moments at the possible hinge locations. What it means, just I have briefed already that, for example, in a beam there are multiple type of loads. It's a continuous point load or VDL. Then we will find against each load the possible failure mechanism, and then we will calculate the collapse load for each against each load, against UDL, against point load, and then the failure definitely will be the maximum load. I will show in the examples, then you will get the more idea how the collapse load works. Then plastic hinges occurs. Plastic hinge formation will happen at the following points at where the maximum moment is present. Definitely in the beam where the maximum moment is present, definitely that point will go under failure when the load start increasing. At the connection involving change in geometry. For example, in a beam, okay, if in a beam one side of the beam have a thicker section and the half side of the beam has a lighter section, for example here is the roller support and here is a hinge support, then definitely the failure in this type of structure due to change in geometry will happen at this location. That is the second point. Under the concentrated loads, okay, where the concentrated loads, for example if there is concentrated load is present here, then there may also chance that failure mechanism also happen at this point. A plastic hinge will occur also at this point. The fourth point, at point of zero shear in span loaded by uniformly distributed load. Means in the beams where there is UDL is present, then at the location where there will be minimum shear, at that point, means at that point there will be zero shear, the plastic hinge will occur. Means at that point yielding will occur. Here is a demonstration. Here is a portal frame. The mechanism, failure mechanism is shown. When the lateral load is acting, a plastic hinge will occur at this point, at the spots also, if that is a fixed spots. Similarly, in the gable mechanism, okay, loading is acting at this point, at the fixed end locations, the plastic hinges will occur. Methods of analysis. For calculating the collapse load, when we apply the load, definitely a certain failure. If we applying the load from this side, the failure mechanism is just like that. If we apply it from top, the failure mechanism will be different. Okay, so how to perform plastic analysis? There are two methods. First one is the equilibrium method or the static method, that is second name, and B is the mechanism method. First, equilibrium method. In the equilibrium method, we simply plot the bending moment diagram of the beam and we point out the location where the maximum bending moment will occur. From that we get the collapse load. That is the equilibrium method. A load computed on the basis of assumed equilibrium bending moment diagram in which the moments are not greater than mp. Definitely the elastic moment that will be less than the plastic moment is always less than or at the worst equal to the true ultimate load. There may be chance that it may at the worst, but it is always less than the plastic moment. Second is the mechanism method or the virtual work method. In this approach, a mechanism is assumed and plastic hinges are inserted at potential plastic hinge locations. Means we identify the points at which location the plastic hinge form. We point out that locations, and then from the method of virtual work we find the collapse load. The method of virtual work is work. The external work done is equal to internal work done. The external work done, that is the externally applied loads, and against that loads actual deformation will occur. And the plastic hinges that happen internally. So work done absorbed at plastic hinges, that is mp into theta, plastic moment into rotation. Here in the equation form, the external load cause deformations in the structure and the internal structure cause rotation in the structure. Okay, that is internal loads. Here the values of collapse loads for different load structures. If that is a fixed ended beam with a point load, then the collapse load value is 8 mp over L. Similarly, if there is a beam with fixed ended beam with UDL, then the collapse load is 16 mp over L square. Similarly for other beams. How to calculate this collapse load? Okay, determination of collapse load. In a simple beam, that is a simply supported beam, and the point load is acting at the spot that is already hinges, actual hinges that are not the plastic hinge. And when the load start increasing, definitely in the simply supported beam the moment come at the center. Due to the maximum moment at the center, definitely the hinge will form at the center of the beam. Then here is the assumed bending moment diagram. Okay, here is the assumed bending moment diagram, that is m of elastic moment and mp is the plastic moment. The plastic moment is always higher than m, so that's why it's just shown above. Okay, and we know from the elastic analysis, if any point load is acting at the center and length of the beam is L, then the maximum moment is W, or if this is a P, then the let me take the pen here, then the maximum moment is that is P L by 4. Okay, P is the applied load. So so in this equation, M is equated to plastic moment. Okay, when it go to plastification after yielding, then we have equated M is equal to plastic moment. Okay, then 4 multiply will the on the other side, L will be divided here, so we will get the collapse load. So here that is the collapse load, that is not the omega, that is simple collapse load, or P, you can name it P. So that's how we calculate the collapse load. Now this is the equilibrium method or the static method, first method. Now we will get the by virtual work. Virtual work, that is the external work done is equal to internal work done. That is the definition of the virtual work method. Now external work done. In the external work done, the load multiplied with the average average deformation or the average settlement. Here that is settlement, if that is the length L by 2 of the beam, and here when the failure mechanism will occur, the beam will collapse and definitely there will be some theta. Okay, if you know this theta deflection and the length of the beam, then you can get the height. just multiply theta with L by 2, you will get this deformation, that is L by 2 into theta. The external work done is load into deformation. So external load is Wu into deformation, that is the L by 2 into theta. Now internal work done at the where the plastic hinge is formed, the deformation is 2 theta. Okay, 1 theta from this side, 1 theta from this side, total theta is 2 theta. So the internal work done when the plastic moment will form, mp into 2 theta. Just simplify this equation, take all the parameters to the other side, theta will cancel out with theta, and again the equation, same equation is formed, that is 4 mp over L. That is same equation we got from equilibrium method. Now the same equation we got from the virtual work method. In this method we equated the equation in the form of external work done is equal to internal work done. External load multiplied with the average settlement and equal to internal movement or the internal plastic movement form and the internal deformation. The internal deformation at that point where the plastic hinge is formed, that is 2 theta. Now take another example, fixed ended beam with the UDL. Now in the fixed ended beam, I have discussed in the first lecture, when we draw the moment diagram, the maximum moment will occur at the spots, that is omega L square by 12, and at the center the maximum moment is the omega L square by 24. So first of all, plastic hinges will form at the spots. When the plastic hinges will form at the spot, then this beam will act as a simply spotted beam. After forming the hinges at the spot, the beam will act as a simply spotted beam. Okay, so now first of all, by equilibrium method, when the beam after the formation of plastic hinges at the spot, this will act as a hinge, this will act as a hinge, then the moment will transfer to the center, and the maximum bending moment diagram will get omega L square by 8 is equal to 2 mp, because that is after the formation of plastic hinges at this location, and at this location after formation of hinges 2 times, first of all at the spot and second time at the center, that's why it's equal to 2 mp equal to omega L square by 8. So 8 take on the other side, divide by L square, you will get the collapse load, that is 16 mp over L square. Now second, by virtual work method, that is the external work done is equal to internal work done. First of all, what is the internal work done? You can see there are 3 hinges are forming, one plastic hinge here, one plastic hinge at right, and one plastic hinge at this. The deformation at this plastic hinge, that is theta, at this plastic hinge, that is also theta, because that is symmetrical, same theta, and the plastic deformation, internal deformation at this center, that is 2 theta. So mp into theta plus 2 theta, that is the internal work done. Now let's see the external work done. In the external work done, the load, that is the W into L. Okay, you just cancel out these two, that is total load, that is the omega L, omega into length of the beam. Then you will multiply the average settlement. In this fixed ended beam, you will get the average settlement by 0 plus this deformation. This deformation is we already shown in the first example. How we calculate this deformation, that is the if we know theta and the length of the beam, that is L by 2, then we will get L by 2 theta at this location. But at this spot, the deformation is occurring, so we will consider the average settlement, that is 0 plus L by 2 theta. 0 plus L by 2 theta divided by 2, that is the average settlement. After L by 2, that will multiply with 2, that will be L by 4. Okay, L by 4 will go on the other side. Okay, then L will come down, this L will also come down, that will become L square. The answer will be omega into 16 mp over L square. In this beam with UDL, we taken the average at this location because the load is distributed on the all over the beam. If the load is present on at the center, then we do not need to take the average. Okay, the load is distributed to the all over the beam, so that's why the average settlement is deformation is taken. 0 plus L by 2 theta at this location divided by 2. Now take another example, fixed beam with the point load by virtual work. In this example, the load is applied is center. Okay, you can simply omega into L by 2 into theta, that is the external work done, and the internal work done, definitely plastic hinge will form at this location, this location, this location. Okay, and the internal moment is the mp into theta plus 2 theta plus theta. You will get the omega, that will be equal to 8 mp over L. That is the collapse load for fixed ended beam with the point load at the center. Now fixed beam with the eccentric point load. Okay, now on the left side there is a greater height, that is A, and on the right side there is a smaller length, sorry, that is a B. That is the bending moment diagram. Okay, in the support negative moment, and at this under the load also there is a positive moment. First of all, hinges will form at the support, then at the center. Now here by virtual work, that is the failure mechanism, hinge will form at the spots, then at the center. Now first of all, now that is not the symmetrical, so theta at this location will be different. Theta 1, that at this spot, that is the internal deformation, at this spot internal deformation, and the total deformation at this center, that is the theta 1 plus theta 2. Now the internal work done, that is the mp into theta 1 plus theta 2, and at the center theta 1 plus theta 2. Now for the external work done, here is the theta 1 and this length is a, then this deformation will be a into theta 1. Okay, now if we multiply theta 1 to a, we get this deformation. Similarly, if we multiply theta 2 with b, we will also get the same deformation. So we can say that a into theta 1 is equal to b into theta 2, and theta 1 calculated will be calculated as b over a into theta 2. Now put the theta 1 value in this equation. Okay, you will get 2b over a into theta 2. Then just simplify, take b over theta 2 on the other side. Okay, then again just by simplification, mp and 2 is taken common and take the LCM, then you will get this value 2 mp a plus b over into a into b at the bottom, and a plus b is the total length of the beam, so that's why here put it as L. So that's how we get the collapse load for the varying length in the fixed ended beam. Proposed cantilever with point load at mid span. Okay, here probed cantilever beam, that is a fixed ended on the one side and the hinge or roller on the other side, that is the probed cantilever beam. Okay, here definitely here is already hinge, real hinge, and due to loading the internal hinge will form at this location and this location, then the failure mechanism will form. Now by virtual work, external work done is equal to internal work done. Okay, external work done, that is the W into, if this length is L by 2, that is L by 2 into theta. Now internal work done, the hinges will form at this location, so that is a theta and that is a 2 theta, so total will be 3 theta. and just simplification, that is W is equal to 6 MP over L. So that's how you calculate the collapse load in different beams. Now for the good understanding with taking values, I will perform the plastic analysis in the beam with the different load values. Okay, for example, here example number 1, consider the beam loaded as shown, that is a continuous beam, fixed end at this port, roller and roller, and with the loads 20k, 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 4 feet, 4 feet, 4 feet, and this span beam, that is 12 feet, 8 feet. The independent possible mechanism along with the potential hinges locations are shown. Okay, their plastic hinge locations are shown, but we can find by our own. Okay, first of all we will assume that plastic hinge will form under first load. If this is a beam, first of all we assume that plastic hinge will form under this first 20k load. Then second chance that plastic hinge will form at this second 20k. Okay, that is shown here. The third possible mechanism is that the plastic hinge will form at the under this point load. That is the possible three mechanisms. Okay, so degree of indeterminacy of this structure, that is 2. So number of plastic hinges required for the failure mechanism, that is 2 plus 1 equal to 3. Okay, for example, this beam, this left span beam, to failure of this beam, one hinges already exists, so we need two hinges for the failure, one hinge under this load and one hinge at support. Okay, so two more hinges are required. So first possible here, second we will calculate the maximum collapse load for each mechanism, and then from all these three mechanisms we will get the maximum collapse load, and that will be the failure load. First of all, mechanism 1. When the mechanism 1, okay, that is, let me zoom out some little bit. Okay, here mechanism 1. Okay, when the mechanism 1 is formed, if theta is on the left, due to the hinge formation, theta is the rotation at this port, then the length of the beam up till that point, that is 4. So the deformation at this location will be 4 theta. Okay, similarly, to get the deformation at this point in the first mechanism, I am discussing currently only the first mechanism. Okay, now in the external work done for this beam, there are two loads. First load, that is a 20k into the deformation, that is a 20k into the deformation, that is a 4 theta. Now at this beam also 20k is also present. So to get the deformation at this location, if 4 theta is this height and the length of the beam on this side, that is 8, then by symmetrical triangle, what will be the height at 4 feet? Definitely that will be 2 theta. Okay, from this side. So 20 into 2 theta, that is the external work done. Okay, by the loads. This load and this load, that is a 20 into 4 theta, and 20 into at this location the deformation you can get by the similar triangle. 4 theta into 8, then what will be this height with the 4? We know this length. Okay, the value you will get, that will be 2 theta. That is the external work done. Now what will be the internal work done? If this is the theta, okay, then what will be the theta value on the other side? You can again get by the similar triangle. Okay, 4 theta over 4, that is the uh, on this side. To get the theta value on this side, you will get 4 theta divided by 8. So 4 divided by 8, that you will get theta by 2 on this side. So the internal work done, that will be MP into theta plus 1.5 theta plus theta by 2. mp into theta, mp into 1.5 theta, mp into theta by 2. After simplification, 120 theta on the left side, 3 mp theta on the right side. The mp you are getting the maximum plastic moment, that is the 40 cube feet. In the second mechanism, that is here, the if the theta at this location, then that length is 8, so you will get at this point 8 theta. Okay, and to get the deformation also in the second mechanism at this location, if that is 8 and that is also 8, so at 4 feet here will be 4 theta. Okay, by similar triangle you can get the value at this load. So first of all, in the second mechanism, external load, okay, due to this load at this point the deformation is 4 theta, so 20 into 4 theta. The second load 20 into 8 theta. Okay, on and the internal hinges, here is theta, and on the other side you can get easily by similar triangle or just dividing length 8 theta by 4, that will be 2 theta, and the total internal deformation at the center will be 3 theta. So here mp into theta, mp into 3 theta, mp into 2 theta, so total will be 6 mp theta on the right side and 240 theta on the left side. So mp value, maximum plastic movement you are getting, that is 40 cube feet. Okay, now in the third mechanism, okay, here you can see the total length of the beam, that is 8 feet, and that is just not on the scale, so left and right lengths are same, 4 feet and 4 feet on the both sides. So due to the symmetrical theta and the internal deformation will be 2 theta, and the center deformation you will get theta into 4, that is 4 theta. So just I am putting the values, 20 into 4 theta, that is the external work done. For the internal work done, mp into theta, mp into 2 theta, and that is a real hinge, so that's why 0. There will be no plastic hinge will form, that is already real hinge, that is why 0 into theta. So you will get mp value, that is 26.67 cube feet. So minimum collapse load or the maximum mp will be the collapse mechanism. So mp 40 cube feet corresponding to mechanism 1 or 2, that is by chance is same. So if there are multiple 5 or 6 mechanism, so maximum plastic moment will govern the minimum collapse load, or maximum plastic moment will be the collapse mechanism. So you can state this sentence like that: the minimum collapse load means the loads which are applied on the beam, uh, that are the loads which are causing the maximum, or you can also state just like that, the maximum plastic movement maximum mp will be the collapse mechanism, mp is equal to 4 cube feet, or this mechanism is forming against the 20 kip load. Okay, so that is a minimum collapse load for the plastic or the mechanism formation. So that's all for today's lecture. Have a nice day.